In the previous video, we talked about cobweb plots, we talked about fixed points. So just as a quick recap, if you have a map here, f of x, and you want to calculate the orbit of a certain initial point, what you draw is you draw the line y equal to x, and then you do a construction like this, which will tell you where you end up eventually. So we talked about the fixed points as being the intersection of these two lines. And we've identified here for the logistic map that you had one at 0.5. But of course, if you look carefully, there's another point where these two curves intersect, and that's the origin. So the origin is another fixed point of this map. If you plug in 0, you keep getting 0. Now, interesting to compare here is what happens if you slightly perturb this, this equilibrium situation, this fixed point. So what happens if you move slightly away from this fixed point 0.5 over here? You see, if you repeat the cobweb diagram construction, that even though if you slightly perturb that situation here, you still end up in the same fixed point. So this is why they call this fixed point a stable fixed point. So over here, you have a stable situation for this fixed point. This is not true for the other fixed point, the origin over here, because here you can easily verify that if you move away slightly from the origin and then you construct your orbit again, you actually run away towards the other fixed point. So this guy over here, this fixed point, excuse me, this fixed point is actually an unstable fixed point, because as soon as you move away slightly from it, you just run away. So if you want a mechanical analogy, a stable fixed point is something like sort of like a ball sitting in the center of a valley. So if you perturb this a little bit, it will move back to the center of the valley. Whereas the unstable fixed point is more like a ball sitting on top of a mountain. And if you then slightly perturb this ball, yeah, then it will just run away and never go back, excuse me, to the top of the mountain. So this is the difference between stable fixed points and unstable fixed points. Obviously, in real life, you will never observe an unstable fixed point, because in real life, yeah, there's always noise that will kick you out of that unstable fixed point. So the stable fixed points are, of course, much more interesting to look at. Finally, a bit of terminology, stable and unstable fixed points. It sounds a bit boring, so this is why people have looked for more poetic names for these structures. So a stable fixed point, they call this a sink. Yeah, think about your bathroom sink, which if you have a hole here, this will attract all the water towards the hole and it will drain out that way. So a sink is something that will attract orbit, so therefore it's called stable. So that's the sink, stable fixed point. And to keep with the bathtub analogy, the unstable fixed point is called a source, because if you have some water flowing out of a source, then the flow lines will move away from the source. So a bit of terminology, sink, source, stable and unstable fixed points. So this was just the intuitive terminology. Let's see if we can make this slightly more mathematically rigorous with the definition. And for the definition, we need to rely on a concept which is called the epsilon neighborhood of a certain point. So the epsilon neighborhoods and epsilon of a point, and in our case, we're interested in the epsilon neighborhood of a fixed point P, is just simply defined as, in our one-dimensional case, as a set of numbers which are at most a distance epsilon away from the point that we're interested in. So you can write this as follows. So it just means that if you have a fixed point P, the epsilon neighborhood of that fixed point P is just the collection of points between P minus epsilon and P plus epsilon. Okay, so this is what we mean by an epsilon neighborhood of a fixed point. Now the question is, can you use this concept to come up with a formal definition for a sink? And that's an interesting thing to think about, so pause the video and see if you can have a formal definition of a sink using this epsilon neighborhood. So if you're pretty far away from your sink, yeah, then you can't really guarantee that you will end up with your map back in that sink. So it's possible that you move away. If you have, for example, a point very far away from P, it's pretty possible that you will not end up at P. But if the fixed point is stable, then at least if you get very close to P, you should be in a situation where if you start close enough and you keep on applying the map, that you will move ever closer and closer towards our fixed point P. So at least there should be some sort of small neighborhood around our fixed point P. So this means there should exist a small number epsilon, such that if you look at all of the points within that epsilon neighborhood, such that for all x within our epsilon neighborhoods of the fixed point P, that if you keep on applying the map an infinite number of times, that you will eventually end up at the fixed point. So this expresses indeed that the fixed point is stable. So for these points in the epsilon neighborhood, we should have the situation that if you take the limit of applying the map k number of times, an infinite number of times in this case, so if you have k towards infinity of fk of x in this small neighborhood around P, that this limit will end up at the fixed point P itself. So indeed, this definition captures our intuition that we built up about the sink, the stable fixed point. Question is, can we have a similar definition for a source? So this was, of course, our sink. For a source, well, we could think of writing down something similar. We could say, okay, there should be a small neighborhood around our source, such that for all values within that epsilon neighborhood, we should have the situation that if you take the limit of k being applied an infinite number of times, of the function, sorry, being applied an infinite number of times, that limit should be different from P. So this is a very plausible way of making a definition for a source. However, it's pretty wrong. And the question is, can you think of at least two possible reasons why this definition does not make a lot of sense, or at least needs some sort of tweaking? So a first problem that you might have identified is the fixed point P itself, right? Because P maps to itself, regardless of the fact whether you have a stable or an unstable fixed point. So we should at least exclude P from our epsilon neighborhood, because that will be the odd one out. This will be one that will move towards P rather than running away from it. Okay, that's one problem fixed. However, there's a more subtle problem, and it's a bit nitpicky here. But the thing is, what we write down here is a limit of the orbit. The thing is, in practice, we're not even guaranteed that this limit exists, because it's quite possible, as we will see in later examples, that if you look at an orbit, that orbit will just keep on bouncing back and forth in the domain of possible states of your system without ever settling down on a single limit point. So we should have a definition that does not really rely on the fact that a limit exists here. So this is something we should tweak. But what we could say, for example, is that, okay, if you keep on at least applying the map long enough, that eventually you should move out of this epsilon neighborhood and never come back. So that's a more rigorous way of writing this definition down without relying on the fact that the limits of the orbit should exist. So we can write something like, okay, there should be a certain number of applications k of our map, such that if you go beyond k, that in this situation, our map f applied k times to a point within our epsilon neighborhood will eventually move out of that epsilon neighborhood of P. Okay, this is a slightly more formal way of writing down the sink and the source here, but the most important points here is just the intuitive graphical concept, sink attracting orbits being stable, and a source repelling orbits, therefore an unstable fixed point.